Hello everyone, this is Héctor, your AFM expert at Nanosurf. This week we'll be looking at pollen from flowers, but not these flowers, these ones, taken from the outside of Nanosurf headquarters here in Switzerland. As you remember, last week we looked also at pollen with the AFM. However, in that occasion, I didn't show you how to prepare the samples. We look into that this week. Also, I will give you a couple of tips of how to optimize your WaveMode signal. Follow me into the lab. So this is how I prepare the glass slides. You get some clean glass slides, like this. Then you get some double-sided tape. It doesn't matter which tape you use. Just glue it on top. And then from one of the corners you carefully peel off the top of the protective side of the tape, and then it's ready to capture pollen. I am outside of Nanosurf headquarters in Switzerland to collect some pollen from the local flowers. To do so, I have a common daisy and a glass slide with a double-sided tape. To collect the pollen, I smash the daisy against the double-sided tape. This harsh movement releases the pollen from the daisy, which then gets attached to the double-sided tape. And now let's see how this looks under the microscope. I'm going to start with the Veronica chimendris, also known as the Germander speedwheel or bird's eye. This was the most difficult of all because it doesn't produce a lot of pollen. If you look at the plant, you can see that it only has a couple of stamens, and this only produces very few grains of pollen. An interesting fact of the Veronica chimendris is that for a long time it was thought that it can cure the gout. So during the 18th century, it was almost eradicated around the London area. Here there is an image of an optical microscope image of the pollen, and you can see that the pollen looks almost like coffee beans. And you can see there is very little amount of it because I only managed to capture these two images, these two grains of pollen together in one single image. How it looks under the AFM? Well, it is something like this. It's full of folds, not periodically arranged, not geometrically arranged. They look kind of random to me. So I wonder if these folds are natural, they have some purpose, or is because the pollen is dry and once it's hydrated they will expand. This is a little bit of a question at the moment. The next flower is called Zephyrantes. It comes from the Greek word Zephyrus, which means god of the west wind. It is common to find it with different colors because there is many varieties of this plant, and it has been used for medical purposes in many different cultures. On this next image, you can see an optical microscope view of the AFM probe close to the pollen grains. It's nice that there is more pollen grains than the previous flower, because whenever we have pollen grains next to each other, they help to keep the neighbor pollen grain stable, which helps doing the AFM imaging. Here you can see a little bit of the surface of the Zephyrantes pollen grain, and you can notice that it's full of tiny holes. It is nice that they are not ordered and they are not symmetric, because otherwise it will be triggering some phobias. But it's a little bit unclear to me what's the purpose of these holes. A couple of hypotheses that I have at the moment is that maybe they help the water getting inside of the pollen, or maybe they help keeping the pollen dry. Maybe they also help whatever is inside of the grain of pollen to go out, or maybe they help creating pockets of air if the pollen gets into water.
Another hypothesis is that maybe these holes help to create an optical effect to attract insects. If you know the answer, let me know in the comments. How it looks under the AFM, the full grain, this is the image of it. As you can see, the distribution of holes is not uniform. It seems they tend to accumulate towards the middle, and at the bottom and top there is few holes or almost no holes at all. This is also interesting. I don't know if it has some structural meaning for this, but I will be interested to hear your comments. So this is how the images of this seed were taken. As you can see, I am using WaveMode NMA, and this is because I want to show you the interaction curves both in time and in respect to the distance to the sample. On the bottom widget, you can see WaveMode settings. What is important in this case is to have a large amplitude to make sure you are completely detaching from the surface when you move to the next pixel. And this is why I got an amplitude of about 2.5 volts. Usually when imaging flat samples or things that have maximum 100 nanometers step, you don't need this much amplitude. But in my case, I need to do that. Second important thing is that your baseline, basically your interaction curve when you are not in contact with the surface, needs to be as flat as possible. Flat means that there is no long range interaction, or that your reference curve already takes this into account. As you can see here, there is a little bit of ringing, which is normal because we are in air, and when the probe detaches from the surface, this abrupt force creates a ringing on the probe, and it takes a little bit of time for it to dissipate. If you now look at the force versus distance curves, you can see that it is flat when the probe is far away from the surface. We have a little bit of a snapping, which is common for these biosamples because there has to be some liquid on the surface, or in general the surfaces are sticky. Then we have a flat indentation curve. Flat meaning that the slope is constant, which is good. And then we have a little bit of relaxation of the surface. This is why the retract curve in blue doesn't match exactly the advanced curve. And we have a little bit of adhesion. I wanted to take these WaveMode NMA measurements because maybe they will give me a little bit of insight of what's going on with so many holes. I was hoping that maybe the surface will be stiffer close to the areas with the small holes, and softer where there is large ones. But I couldn't see any difference. So if the holes has a purpose, I'm almost convinced that it isn't structural. It has to be functional for some other reason. The next one is the Bellis perennis. It's my favorite, also known as the common daisy, or also known as the national flower of the Netherlands. This has a lot of pollen. You can see in this optical image that there is so much pollen that it starts to pile up on top of each other. So in a way, this was easy to image because the pollen was helping. The pollen grains were helping each other to stay in place. But you will see in a moment it was also very, very difficult. One of the reasons is that the size of the pollen is comparable to the size of the AFM probe, and this makes it difficult because then you start to hit the pollen with the cantilever, with the size of the probe. You get a lot of artifacts. But there is even another complication. As you can see now in the AFM image, this pollen is covered with spikes that can be as large as 5 micrometers, which is a size that it can create problems with the AFM probe. If the spikes are lying, let's say, vertically, the AFM probe can image them easily. But if they are at an angle, in the best case we get an artifact instead of an image, and in the worst case we might end up breaking the tip because it hits the spike laterally. So this image doesn't look very good, but it's also very difficult to image it. The next one is the Ranunculus bulbosus, or bulbous buttercup. It's a yellow tiny flower, and I will show you first the AFM images, and I will let you see the grain of pollen later on, because I want you to see something. First of all, look at this. This is a 3D view of the AFM image, and it shows a thorn, a spike. And what is cool about it is that it has these tiny holes around the spike. I cannot figure out what are these holes for. I was speculating with the other flowers, got some ideas for them. In this case, I have no idea. Maybe the thorn is to be attached to a bee or to another insect, and the holes release something into the bee or in the air when the bee is flying around. I have no idea. But as you can see in this other AFM image of the whole grain, it's fully covered on these spikes and the holes. And what is cool about it, here you have more images of the pollen. What is cool about it is that, as you can see here in the optical image, it has an iridescent effect on it. And I think this is because of the many spikes and the many holes, creating some sort of light interference, and then decomposing the light in these different frequencies, which I think is really cool about it. Not sure if it helps the insects to get attracted to it. Probably it does, or if it has another function. If you know, let me know.
Hopefully you have enjoyed this Friday AFM. Let's recap what we have seen. It is possible to prepare pollen from this type of flowers to look at it on the AFM. If you remember, we need a glass slide with double-sided tape, and we can smash the flower against the double-sided tape. This is enough to capture the pollen. In some cases there will be a lot of pollen, so you need to look for areas where there is only a few grains together. In other cases it will be very difficult to find the pollen because there is not so much. One trick to get good images is to look for the grains of pollen that are close packed together, so if one tries to move, the other one will keep it in place. In terms of wave mode, it is good to have a large amplitude for this type of samples, but you need to make sure that you have a clear background, meaning that your signal needs to be flat when you're far away from the sample, and you need to have a clear interaction curve when you are touching the surface. It is possible that with pollen that you have a lot of surface attraction. There will be a little bit of snapping and a lot of adhesion. Just make sure that your probe is moving up and down enough to get free from this interaction when you move from one pixel to the next one. Hopefully you will try some of this, and I hope to see you next week. Bye.